Hello everyone. So today I want to discuss a little bit about determinant of a matrix and more specifically on what does the determinant of a matrix tell us about the matrix. So let's begin. So first let's look at how a determinant is calculated. In this presentation I hope you're all familiar with basic matrix operations such as calculating the determinant, matrix multiplication. So for a small revision we can see here we are considering a small 2 by 2 matrix with these elements 3, 2, 4, and 6. So for a simple square 2 by 2 matrix, how a determinant is calculated is, so we multiply the diagonal elements and we subtract the product. So here we can see 3 times 6 minus 2 times 4, which gives us 18 minus 8, which gives us 10. So the determinant of the given matrix is 10. But what does this really mean? Here again we have a 3 by 3 matrix. Keep in mind that determinant only exists for a square matrix. A square matrix meaning that the number of rows and number of columns are same. So here you can see how a 3 by 3 matrix determinant is calculated. Again, as I said, I hope you're all familiar with the basic determinants of a matrix calculation. So here we get the determinant of a 6. But again, what does it tell us about a matrix? So what does it tell us? To answer our questions, we need to change a little perspective on matrices. Instead of thinking of matrices as a grid of numbers, we need to start thinking of it as a function. If you know basic linear algebra and if you're familiar with functions, then you know that functions take certain numbers as input and it performs different operations on that input and returns some values. So if you're thinking of matrices as functions, that matrix also performs some operations on given input and results some outputs. So let's take a small example here. Here we have a small example for a linear transformation of scaling. So here the given expression represents the scaling. Here x dash is equal to sx times x and y dash equals sy times y, where x and y are the x coordinate and y coordinate of a original point, and x dash and y dash are x coordinate and y coordinate after transformation, whereas sx and sy are the scaling factors. So you must be familiar with this equation if you have studied basic mathematics. So the above equations can also be written as follows. So x dash equals sx times x plus 0 times y, and y dash equals 0 times x and plus sy times y. So you will be familiar with this expression as well if you have studied computer graphics or just basic linear algebra. So here you can see in the comparison between the two forms of the expression. So first 0 times y results in 0, giving the original value of x dash, and here 0 times x in the second equation results in 0, giving the value for y dash in the original equation. So again, the rewritten equations can be represented in matrix form as follows. Here x dash and y dash, which is a column vector, represents the transformed point. Sx 0 0 Sy represents the scaling matrix, and s sorry x and y represents the column vector for the original point. So in matrix form, x dash equals s times x. So we defined a scaling matrix, so which was sx 0 0 and sy. So keeping values of sx and sy is 2 and 2 for both scaling factors, we get the following scaling matrix. So this scaling matrix scales both the x coordinate and y coordinate by a factor of 2. Now calculating the determinant of the scaling matrix as, here we get 2 times 2 minus 0 times 0, which is equals to 4. So the determinant of the scaling matrix is 4. And for one last time, what does this mean? So we've asked a lot of questions. Let's start answering them. So to answer our questions, let's consider a square ABCD having the coordinates a minus 1 comma 1, b 1 comma 1, c 1 comma minus 1, and d minus 1 comma minus 1 is shown in the graph. Here you can see the graph a, b, c, and d. So each length, sorry, each side having a length of 2 units. So here we can see the area of square ABCD will be 4 square units. The given square can be represented in matrix form as follows. So here each column of the matrix represents a certain point. So first column represents the A coordinate, A point. The second column represents B, third column represents C, and the last column represents D. Here each row represents either X coordinate or Y coordinate. The first row represents X coordinate for each point, and the second row represents Y coordinate for each point. Now, we previously defined matrix as a function which takes certain values as input and returns some values as output. So our original square ABCD is going to act as an input. So we're going to provide ABCD is input to our square matrix S, the scaling matrix S, and we're going to see the output, how how the input is transformed into our output. So here we can see, so by applying a matrix to a certain square ABCD, what we mean by that is we pass each point of ABCD to the square matrix or the scaling matrix S. So here we can see we're performing a basic matrix multiplication. Again, as I said, I hope you're familiar with basic matrix operations. So here when we multiply the scaling matrix S, that is 2 0 0 2, with the matrix representation of the original square ABCD, we get the transformed values of A dash, B dash, C dash, and D. So where A is transformed to A dash, B is transformed to B dash, C is transformed to C dash, and D is transformed to D dash. So the coordinate of the transformed square are A dash minus 2 comma 2, B dash 2 comma 2, C dash 2 comma minus 2, and D dash minus 2 comma minus 2. So let us see what has happened here, how the original square has been transformed. So in the graph you can see our original square ABCD is represented in blue color, and here you can see in the red color A dash, B dash, C dash, D dash is our transformed square. So we scaled the square in both x-axis and y-axis by a factor of 2. Here we can see the square has grown larger. Here you can see the area of the transformed square A dash, B dash, C dash, D dash is 4 times 4 equals to 16 square units, and from previously we know that the area of the original square is A, B, C, D is 4 square units, and we also know that the determinant of the matrix S is 4. Now here if we take the ratio of the area of output shape and area of input shape, that is area of A dash, B dash, C dash by area of A, B, C, D, we get 16 by 4, which is equals 4, which also happens to be the value of our determinant S. So is it just a coincidence? Which is actually not. So what the determinant of a matrix tells us is how a space is transformed by the matrix. So here we can see that the area of the square has been multiplied by 4 times. It is 4 times larger. So which is answered by our determinant. So the determinant tells us how much a matrix transforms or scales an input, or the input space more precisely. But is that all? Now let's see. Now, if you have performed matrix operations, you might be familiar with seeing negative determinants and determinants of zero. So, what do they mean? Now, let's see. So, what if the determinant is negative? To answer this, we're taking a simple matrix M, and the values are set up so that the determinant is negative. Here you can see the matrix M with values 1, 2, 3, and 4. So, the determinant is 1 times 4 minus 2 times 3, which is equals to minus 2. So we have a negative determinant, and as previous we have our original square A, B, C, D. So again, applying the given matrix M to our original square, we get the transformed square as follows: a dash, b dash, c dash, and d dash. So here a dash is 1 comma 1, b dash is 3 comma 7, c dash is minus 1 comma minus 1, and d dash is 3 comma minus 3 comma minus 7. Here you can see that the point 1 comma 1 and minus 1 comma 1 are in both input square and sorry, the input shape and the output shape as well. But in case of input, the point 1 comma 1 is b, but in case of output, the point 1 comma 1 is a dash. So let us see what has happened here. So if you see the graph here, here again the blue square represents our original square and the red shape represents our transform shape. So if you see here, our point A has transformed to where B was, becoming A dash, and our point C has become C dash, and it lies where our original point D was. And here you can see the point B has transformed into B dash, which is at the top of the screen, and our point D has transformed into D dash, which is on the bottom of the screen. So if you notice here, our points A and C has changed quadrants. The point A from second quadrant has shifted to the first quadrant, and the point C from the fourth quadrant has shifted to the third quadrant. So you can think of this as the shape flipping in some way. So the B and D points are in the same quadrant, but A and C have flipped directions. So you can imagine a shape changing its orientation and flipping. So now let's look at the values here. The area of the transformed square a dash b dash c dash is 80 square units here. I've calculated the value directly here. You can calculate the area using the said points and using the formula for area of a polygon. And again, we have the area of original square is 4 square units, and the determinant of matrix M is minus 2. Now, if we look at the ratio here again, so area of A dash B dash C dash divided by area of A B C D, we get 8 divided by 4 equals to 2. Now the 2 is same as the determinant of a matrix modulus applied. So magnitude of determinant of the matrix M. So the magnitude of determinant tells us how much a shape is scaled. But what the negative sign tells us is that the shape has been flipped in some direction. So either by in x-axis or either in y-axis. Here we can see the figure has been flipped along the y-axis. So the sign tells us whether there is a change in orientation in of the shape or not. And the magnitude of the determinant tells us how much a matrix scales, expands or contracts the space. Now what about a zero determinant? So again we're taking our original square, and again we're taking a matrix such that a determinant is 0. So here we have a matrix M with values 1, 2, again 1, 2. So the determinant is 1 times 2 minus 2 times 1 equals to 0. So what does the zero determinant mean? So now again to find out, let's apply the given matrix to our original square. Again our output is transformed to the points a dash 1 comma 1, b dash 3 comma 3, c dash minus 1 comma minus 1, and d dash minus 3 comma minus 3. Now again let's see what has happened here. So if you see the graph, here we have A, B, C, D is our original square in blue color, and in red color you can see the output has been transformed into a line. So here when we passed a square, a 2D shape through a matrix having a determinant 0, it resulted in a line which is one dimensional. So what the determinant 0 tells us is that the dimension of the space is reduced. So here we passed a 2D space along a matrix. So the matrix transformed it into a 1D space. And same is the case for, if we are using, in this case we are using 2 by 2 matrix, so we're only talking about a two-dimensional shape. So if we use a 3 by 3 matrix to represent a three-dimensional shape, then we will be talking about volumes instead of area. So if we pass the cube through a 3 by 3 matrix having a determinant 0, then it would diminish the shape into a square. So a three-dimensional shape is reduced to a two-dimensional shape, and a two-dimensional shape is reduced to a one-dimensional shape. So here, determinant of 0 reduces the dimension of input shape, which can be thought of as loss of information. Now, you must know the formula for calculating the inverse of A, which is adjoint of A by determinant of A. And we often say that if a matrix has a determinant of 0, then its inverse does not exist. Now, what is the intuition behind that? So, we talked of matrices as functions. Now, we know that functions can have inverses. So, what does the inverse of a function do? So, instead of taking input and returning some output, we can take the output values and use the inverse to gain the original input values. And same is the case with A inverse. So, here, previously, we had seen that we could take a shape and we can transform it into some other shape, another 2D shape. So in this case, since our determinant is not 0, a certain matrix exists which is A inverse, that is inverse of the matrix. So the inverse of a matrix can be used to get the original values using the output values. But in this case, we cannot get the original values of A, B, C, D using the output values A dash, B dash, C dash, and D dash, because we cannot create new information out of nothing. We have only information about one dimension in the output, so we cannot create information about another dimension. That is why if determinant is 0, that is our input space is reduced in dimension, A inverse cannot exist. So what does a matrix tell us? It tells us whether a matrix expands or contracts space. It tells us whether the matrix flips the orientation of a space. And lastly, it tells us whether a dimension is lost or not. So, determinant of a matrix is more than just a number. Hope you enjoyed. Thank you.